Hey there. Hi. Welcome to the first discussion of p-values that we'll have in Research Methods and Statistics 2. The point of this video is to make sure that you have a very careful understanding of what a p-value is, because we left off the last video just getting to calculating t for a one-sample t-test. So once you have t, you then are able to move to p. And there's a couple ways to do that. So before I do that, I'll say that every time you move from a test statistic, so in this case our test statistic is t, to a significance value, which is p, you're going to need to go, usually, if we're going by hand, to some kind of table or some kind of lookup system. And if you're doing it using statistical software, it'll pop up right next to it for you. And so when you look it up on a table, you need to know the degrees of freedom that you have in your test. And it differs a little bit by test, but for our one sample t-test, it's very simple. It's the number of people in the sample minus 1. The other thing you need to know for a one sample t-test lookup is the directionality of the test that you're performing. So if you're performing a two-tailed test, you'll remember that as one in which the alternative hypothesis is probably includes a not equals sign. We have no hypothesis about the directionality of our intervention. We think it could go one way or the other. Then you'll have a two-tailed test. But if you have a specific hypothesis about the directionality, so you've got some greater than and less than or equal to, some of that kind of stuff going on in your null and alternative hypotheses, then you might be performing a one-tailed test, and so you would use these alpha levels up top. So we're going to be using the 0.05 level for pretty much all of this course. I'll give you some kind of thought experiment type problems in which you have to consider 0.01, but for the most part we'll be dealing with 0.05, so sometimes 0.05 in a one-tailed test, sometimes 0.05 for a two-tailed test. So you use that to look up the critical t-value, and then you will compare that critical t-value to the t-value that you've calculated, which we call your observed t-value. And so if your t observed is larger than the t critical listed at your level of degrees of freedom and your test directionality, that indicates that the p-value is lower than that alpha level. So it's less than 0.05. So you could technically always look up the 0.01 value as well if you have it, which you would if you had this particular table for a t-value. But I won't really ever require you to do that specifically. We're just going to perform tests at the 0.05 alpha level. I'd say 99% of the time. But anyway, when you have a p-value less than 0.05, less than your alpha level, you have a significant finding. And that's the threshold for being worth talking about in psychology, our p-value being low enough that it is lower than our alpha level. You can get p-values one other way that I find to be quite useful, and that is to use the Shiny apps developed by a psychologist that are available online. So there are a couple of these, and we'll talk about them throughout the semester. We'll use them a few times. But in test statistic, you'll enter the value. So let's say our t is 1.034. And then you tell it that you want a t distribution. And then you will tell it that you have, let's say we're doing a two-tailed test here, and we've got, let's leave it like this, there's 11 people in the sample, so we have 10 degrees of freedom. So with all that factored in, the p-value it gives us is exact. It doesn't tell us whether it's more or less than some other value, so we've got a p-value of 0.2, meaning that we have a finding here that's not significant, so we would fail to reject the null hypothesis. It also gives you Cohen's d, which we'll talk about in a few weeks, and that will become important at that point. This is the same calculator we'll use for all the t-tests we do this semester. You could use it for this one sample t. You can also use it for independent groups and repeated measures t. They're all based on the same distribution of values. So I just kind of started to say it there, but the other big sort of conclusion here is that if your t observed is larger than your t critical and your p-value is less than 0.05 and or they'll always, if one is true, the other will always be true, then you have a significant finding, meaning that you reject the null hypothesis and conclude that there was some effect of your intervention. That second half, though, remember, is not statistically logical. It's just sort of theoretically logical. And I want to caution you against a couple of things in that process. First of all, it's a bad idea to only just look at summary statistics, be they measures of center and spread, test statistics like t, or significance values like p. If you only ever look at those summary values or those comparison values, you can miss out on something important in your data. So here's a cute little example of two different means that have the same standard deviation. The one on the left, we're only looking at the data in summary statistic form, so we don't know what's going on behind it. It's got all our individual data points hidden. And then in the graph on the right, I guess it's embarrassed because it's naked, I'm not sure, but the bar is accompanied by individual data points. And that basically leaves me to the suggestion to always look at your data. Always find the most useful way to display it graphically and by participant if you can, or by individual data point if you can, so that you can get an idea of what's going on inside the data set as opposed to just only ever looking at the summary statistics. And what you'll see sometimes when you do that, and what you will notice other times even if you don't, is that P is imperfect. And though our sort of end goal in most of our step-by-step processes this semester is to get to P, it is not the end-all be-all, only stat we ever need, only number we ever want to know. And one major reason that it's imperfect is that it's not very intuitive to interpret. It's technically an indirect measure of probability in that it's the probability of getting results at least as extreme as the ones you observed, given that the null hypothesis is correct. So it's imagining an alternative world where we know the null hypothesis is true and telling you how likely it is that you got differences between your means at least as extreme as the ones you actually did. So it's a long, sort of complicated, probabilistic situation. And I have the graph on the slide here to show the idea that we're talking, again, about results at least as extreme as the ones you observe. So we're talking about these whole shaded blue areas, if this is our alpha level, these two spots here in a two-tailed test. Anything out here and anything out here all fit within the realm of any given two-tailed p-value. P does not tell you how likely it is that your alternative hypothesis is wrong. It doesn't tell you either how likely it is that the alternative hypothesis is right. All it tells you is the probability of getting data like you did, data as extreme as yours, data with two groups as different as yours were, if, in fact, the null hypothesis were actually true. So if the alternative hypothesis was absolutely wrong, we have the probability of accidentally getting results that are this different. It's somewhat helpful to think of an oversimplified example that I stole from a science writer named Christy Ashwandon. Her example is, imagine that you have a coin and you suspect the coin is weighted to heads. And so your null hypothesis in that case is that the coin is fair. Your alternative hypothesis is that the coin is unfair. It's weighted to heads. So you flip it 100 times, you get more heads than tails. The p-value in that scenario won't tell you whether the coin is fair, but it will tell you the probability that you'd get at least as many heads as you did if the coin was fair. Again, if the null hypothesis were true, the probability that you would get data at least as extreme as the ones you did. It's confusing. It's layered. It's not very intuitive. Psychologists think about this problem all the time. This disconnection between our understanding of P and the way that people talk about P, even within the scientific literature. It's something that we try to make really clear to students in their stats lectures, but people seem to lose over time. For some reason, that this fact gets fuzzy. So here's an example of a psychologist talking about it. He tweeted, "It's incredible to see how often absence of evidence of an effect is still confused for evidence of absence of an effect, even by statisticians or methods-oriented epidemiologists." It's hard for our brain to figure out that when you look at some data set, you actually may not have learned very much. Again, even this first sentence is kind of hard to parse. So he's saying that there is a difference between the absence of evidence for an effect and the evidence of absence of an effect. In the first case, you don't know anything. You don't know anything new. There is no evidence. In the second one, you know that there is no effect. The difference there is just the switching of two words, but it's a completely different meaning in terms of statistics and a completely different meaning in terms of the application of those statistics to the real world. We run into a lot of problems with this when we start to look at the way science journalism works. So it's crucial to think about that really, really slight difference between the absence of evidence and evidence of absence. Let's keep going. This list is adapted from a book I love by Zoltan Dinas. I actually don't know how to say his name, but this is a list of the wrong ways to interpret your p-value. Number 1, P is really, really small, so I have disproved the null hypothesis. That's not true. That's never going to be the case. Another way, P is small, I've proved the alternative hypothesis. Even less true, somehow. When P is small, remember you have evidence that the data that you got are so extreme that they would be really, really rare if the null hypothesis were actually true. You don't know whether it is or isn't. You have nothing to say about whether the alternative hypothesis is or isn't true. But what we do is we make a sort of 3-step statistical leap in our writing in which we say, if the null hypothesis were true, these data would be super unlikely. So because I got them, I think that the null hypothesis is not true, and because the null hypothesis is not true, and I set up this complicated logical scenario, I think the alternative hypothesis is more likely now to be true. We don't say all of that in every single psych paper because it would be cumbersome, and so that has led to a somewhat of a misunderstanding in some parts of psychology. So again, that's why I'm hounding on it here. Another wrong way to interpret P, it is the probability that the null is true. No, definitely not the probability of anything so directly about the null. It's also not the inverse probability that your hypothesis is true, sort of the opposite of the idea that it's the probability that the null is true. If you reject the null, P is the probability that you're wrong. That one is kind of compelling. Like, it sounds really close, but it's still not quite true. If you reject the null, P doesn't tell you anything. If the null were true, P would tell you the probability that you would have data as extreme as you have. Another way people falsely interpret this sometimes is if I did this experiment 100 more times, I'd get the result about 1 minus p times. Not quite. One of the other really clear writers and thinkers on thinking about P and interpreting P is Dr. Daniel Lakens. I've provided this link to you here, these two links on p-values and on hypothesis testing, because I really, really recommend you spend some time with them. They are really, really well put together. He is a really excellent, clear speaker on these kinds of issues. Because I do not want you to leave my course as a statistician who lets the p-value be the lone lead singer, when in fact there are lots of other things that are important to know about any data set. You want to get P out of the spotlight. You want to work on doing really good data visualization. You want to work on thinking about context and any possible correlations. And really soon in this course, we're going to talk about effect sizes as a companion for P. Even further from the issues with P are the issues with this whole approach. I don't want to just completely disillusion you to all that we're going to do this semester at the beginning, but what we're doing is called null hypothesis significance testing, and I'm going to abbreviate that NHST, and it is imperfect. Just like everything else in psychology and in science at large, statistics are worth talking about. It's worth understanding what's going on behind them so that you can understand how much to believe them, how exactly to weigh the evidence that they're showing you. One big issue with NHST is that we're taking continuous, ever-changing things like our data or like p-values or just the general state of the world and trying to reduce them down to one binary decision. We are just rejecting or failing to reject, or if you've written it improperly, accepting one or the other hypothesis. And when you do that, it doesn't tell you much about the real world. It just tells you a really specific answer to a really specific question. It doesn't tell the reader whether to believe like 100% with their whole being that something is true, or if maybe you're like 50% sure now that something is true. There's no statement of that. We don't talk about how sure we are of some outcome. We just say, here is exactly what happened here, and this is the way it happened. It doesn't help for outside application all that much. Another big issue is that researchers can pick any level as significant. They can choose their own alpha level. Most stick to industry standards, but once you've chosen a level of significance, you can't then interpret, by the logic of the system itself, how much smaller the p-value is than that level. So if you choose an alpha level of 0.05 and then your data produce a p-value of 0.00001, all you can say, and still have your NHST logic intact, is that p is less than 0.05. Again, it is so binary that it's practically suffocating. We can't say very much about our data and the continuity of our data at all, and it makes it really hard to take these things out and apply them to the real world. Paired with that is the one written on the slide here, which is the fact that alpha and p compound when you run more than one test. So if you run a study that requires you to run a couple of t-tests at the end, if you run those all at an alpha level of 0.05, if you run enough of them, one of them will eventually turn up significant, and not because it is a real effect, but because you've falsely generated a type 1 error. We'll talk more about that problem later on. Third big issue with NHST is that most hypotheses, due to the structure of the form, are that there is no difference between two groups. We say like, okay, so in the examples we've talked about in the past in this class, I think that B vitamins will make children score higher on IQ, and so my null hypothesis is that the two groups, the children who took vitamin B and the children who didn't, are going to be the same. There will be no difference. And so what that means is we're only testing to find any difference, regardless of whether it is a difference that's large enough to be interesting in the real world. So it sets us up to find things, to have findings, so to speak. But when you design what's called a point null hypothesis like that, in which your null hypothesis is that there is no difference, it's so specific that it's pretty likely to be false. So you've set up your alternative hypothesis then as quite likely to be true, which some philosophers of science argue is not really worth doing. If you're going to do worthwhile science, you should be designing hypotheses that are, rather alternative hypotheses that are easy to disprove, not difficult to disprove or easy to find evidence in favor of. The particular philosopher of science I'm thinking of here is Karl Popper, who I recommend you go watch this YouTube video to sort of learn his general approach to science. We may read more about him later in your semester, but in general, this is kind of the wrap up to this short bit on why P and null hypothesis testing can lead people astray. It is it's designed very specifically, and its logic only allows for very certain conclusions, and some argue that it can push you toward making uninteresting conclusions when you do even reach them. So keep all this in mind going forward. Pay attention to ways we talk about to get around and to take the spotlight off P, and we'll have you heading into the new decades and century of science as a more contemporary user of statistics.